Anyone did this integral, by the way? So let me just go for a quick recap. So what we did. So basically, you found we reviewed what we called piecewise continuous functions. Then exponential order. So basically what this function is exponential order means. So simply this means it so your function, as time goes to infinity, it will not increase very rapidly. So it will not grow faster than the exponential function, exponential t. Okay. So because of that, you can use this exponential function and control that the other function. So once you multiply by minus exponential minus st and integrate, so once you do once you multiply by my exponential minus st, you are tracking that the other one so that's the idea. So and when you integrate, so that the integral converges, so Laplace transform exists. And also we looked at what we call improper integrals, and we show they may converge or not, or diverge, right? So that's why it is important. Then, so I think I did not review, but because we have done this in school, something useful here is the partial fractions, and of course integration by parts. So once you have a good idea about these things, then we can define what we call the Laplace transform. So basically, what was the Laplace transform? You have this function. So when you say good function, nice function, will it be a good function? We mean this function which if you look at that theorem, they are given. But so when you work in engineering, all the functions you get, usually you work with what kind of function? Sine function, cosine function. So couple of things to remember. So when the given function is f of t, so usually our variable is time. So you take this function, multiply by exponential minus st and integrate at 0 to infinity. So this is with respect to t. So this is what we call the Laplace transform of function little f of t, and our regular notation is we write this as capital F of s. Okay. So s is I mentioned s can be complex number, but for this class s is a real number. Okay. So s is a real number. So s can be a complex number. So the couple of things to important things to note here. So see the given function I will show you I mentioned at the beginning of the class, but because this is important, let me rewrite here again. So after this lesson, so you should be able to do these three things for sure. Okay. Now I think I showed last time there is a table. Now I am not sure you have done this question or not. If you look at table, most of the time you can find, but in the mathematics class you should know how to do this by hand. Okay. So here, so the given function 1 over square root t, we wanted to find the Laplace transform. Okay. So let me show that. So our exercise is to do this calculation. Now this is just an integral, right? So Laplace transform of 1 over root t. So integrate 0 to infinity. So all you have to do is do this integration. But if you try, this is actually talk about this kind of question so that you have some idea. Now to do this, let's say we use a substitution. So let's say st take as tau. So when your lower limit 20 is 0, so tau is 0, upper limit. So when t approaches infinity, tau approaches where? Tau is s times t. Now remember we said s is a real number. So when t goes to infinity, st goes to where? So that's why here we impose one condition. So we want this to go to infinity. So we say this is if s is strictly greater than 0. Okay, now that's an assumption, which means whatever we do after this in this calculation, this is our condition. So s is so far strictly positive. Okay. So in this integral, now s is, remember s is a constant. So what is dt? maybe you should try to do at least. So 1 over 1 over t is s over t over tau. So note that in this integral s is constant, so you can take that out. So you have tau minus 1/2 . So this is what we get. Okay. Now this doesn't look like anything you can something new, probably. So there is something called gamma function. So this is capital gamma. So this is a definition, okay. So we define this as so this is basically this decaying exponential function, and multiplying with say x to t minus 1, and note that your variable integration here is x. Okay, so we have this polynomial being multiplied by decaying exponential function and integrate. So this is a special one reason I do, I'm not sure whether you will need after this lecture or not. So this is the gamma function, and here note that if you have t equals 1/2, so this value we can show mathematically. This is going to be square root pi. Okay. So now note that actually that's the when if you put t equals 1/2, that's what you have here. Okay. So don't get confused with the variable of integration. So this will become square root pi. So pi over s. Everything square root. Note that s was strictly greater than 0. Okay. Okay. So this may be something you can, if you didn't follow you can check this later. Okay. So my point was, calculate the Laplace transform of P. Okay, I think so. If this looks like kind of different, well, maybe the first time you are working with a special function, so that's why. Okay. Next here I have written the inverse Laplace transform. So now what's happening here? Say we had this function little f, right, in the time domain, and this object, so we put into this kind of object. So which did this the Laplace transform. Okay. So once we are given this one, so this Laplace transform, so it gives this function. Okay. So inverse Laplace transform means the going from in the other direction. So if you are in the frequency domain, f of s, this function, and if you want to go this way, so this is called the inverse Laplace transform. Now inverse Laplace transform I will when you integrate things, say we now that usually we find this from tables. We are not going to calculate mathematically. I mean, there is some formula which is complicated using complex analysis actually. So if we have this kind of function, so this is a causal function, so this part is 0. suppose you have this function, let's say this is just t, ramp function. So I hope you have done that. Ask you to complete the Laplace transform for t when t is positive. I hope you have done that. So here you get Laplace transform of t to be 1 over s. Okay. So we are going to say inverse Laplace transform of t, 1 over s to be t. Okay. Now thing is, if you calculate this for this kind of function, you end up with the same answer for your integration. In practice, I think you are not going to worry about this kind of situations, so you don't need to worry too much about that. Okay, so that's why you can straight away go for this table here. Now the given function is, we want to find inverse Laplace transform of s over s squared plus 4. So using a table, I think you have a table with you. What do you see here? So the given function s over s squared plus 4. So what's the inverse Laplace transform? So altogether there are 4 columns. Okay. Now there are altogether, I don't know, 33 functions here, but mostly you may work with like 5, 6, 7 or less than 10. So note that the given function was s over s squared plus 4, right? Now here you will see s over s squared plus k squared. So that's what the function now you need to look for, right? So in this left hand side, this is the given function f, and this is your capital F, the Laplace transform. So when you want to find the Laplace transform of some function f, you look at the function and Laplace transform is right hand side. Want to find the inverse Laplace transform, so these functions are in terms of s, so that's the Laplace transform. So you may not find all the time exactly the function given to you. Read the corresponding original function. So here what's going to be? So this is, if the Laplace transform is s over s squared plus k squared, given original function is cosine kt. So when it is s over s squared plus 4, what's the function? Which means you just need to figure out what should be k. So k should be what? So this is just pattern recognition. So even you have no idea about Laplace transform, still you can use k is 2. Yeah, good. So if k is 2, you get s over s squared plus 2 squared, which is 4. So that's what we're going to write here. So we have from table. So Laplace transform of cosine kt is s over s squared plus k squared. So when k equals 2, you get Laplace transform of cosine 2t. So s over s squared plus 2 squared, which is s over s squared plus 4. So this is the Laplace transform. So inverse Laplace transform is now this one. Okay. So answer here is cosine 2t. So is this very clear? I mean, this must be 100% clear. Okay, let me give you one. So this is for this one, exercise 13. So we asked to find, so find ft. So f of s, now please change this 3 to 1. So 1 over s squared. So find little f. So can you tell me so table here. So that's where you have to stop. So right here. Now here when n is 1, so that's 1 over square. Okay. So which means here when n is 1, right hand side Laplace transform you have 1 over squared and the original function is t to the 1 which is t. Okay. So all you have to do, so write this as, so f of t is simply t. So this is from table. Okay. So from the table we had Laplace transform of t to the n to factorial n So earlier I think somewhere here so this is actually a square. Okay. Okay, now this is clear up to here. Inverse Laplace transform. So we did a couple of examples. If you understand how to do that, okay, now Laplace transform comes with very nice properties. So we will look at the most important ones. So this is what we call the linearity. So this tells if you have two functions, now here I have written little u and little v, and for each of those functions, if the Laplace transform exists, it means you do the integral and the whole. So then we have but here we are saying two things. So if you have two functions u and t, so this tells so one, if you add two functions u and v and take the Laplace transform, it would be same as you take the Laplace transform of u and then add Laplace transform of v. Okay, and so this is a special case when you select alpha and beta to be 1, and if you select beta to be 0, you get the scaling property. So if you multiply when alpha is any real number ut and do the Laplace transform, you can take this alpha out, Laplace transform of ut. Okay, so these are the two things we are saying. Now I may not want to prove all these things all the time, but this is kind of important and also easy, so let me show you how to prove this. So you start with left hand side. This is sort of proof. Now this kind of thing actually you should be able to do. So you start with left hand side, and can you show this? Can you get the right hand side? So how do we calculate Laplace transform? Integrate 0 to infinity whatever inside. So this is alpha times ut plus beta times vt with respect, and you take the function, multiply exponential minus st, integrate with respect to t. Okay. Now you can rearrange things. This you can do actually when you have this improper integral. This rearrangement is possible when each integral converges. So alpha is a constant, you can take that out. So 0 to infinity, this is ut, here multiply exponential minus st dt. I am going to add, beta is a constant, take that out, 0 to infinity, this is vt exponential minus st dt, and what is this? This is nothing but alpha, this is the Laplace transform of ut, and times plus beta times, this is Laplace transform of et, so that's our right hand side. Okay, so very simple, straightforward proof. Note that this is possible. We are doing this separation since each integral converges. Now straight away we have an application. So Laplace transform of 1, I think we found last time, and we better remember. So we are recalling that, and Laplace transform of exponential at 1 over s minus a. So these two things are given. Laplace transform. So how do you find it? So one way to do, you can integrate, of course. So here you can do this if you want. First let's say Laplace transform of 6 here. So plus or minus, so if you put minus here, Laplace transform, you have 5 exponential 4t. So 6 we don't know, but 6 is 6 times 1, so you can take 6 out. So this is 6 times Laplace transform of 1. So 5 is a multiplicative constant, you take that out, Laplace transform exponential 4t. Now the Laplace transform of these two functions you can find in the table, or they are given right here. So Laplace transform of 1 over s, so here 6 over s minus 5. So exponential 80 1 over s minus exponential 40 1 over s minus 4. Okay. So this is your answer. So maybe you want to say now this is a new function in the s domain, so what's the domain here? So domain is strictly greater than 4. Okay, now in the same way, for the inverse Laplace transform also you have linearity. Okay, so the same, which means if you have now capital U in the S domain, capital V in S domain, if you have alpha times U plus beta times V, inverse Laplace transform, it is same. If you know the inverse Laplace transform of U separately, and so please make this V here, so V separately, then you can add those two and take the inverse Laplace transform, will be same as take the inverse Laplace transform first one and add the inverse Laplace transform. Okay. So scaling also the same. So couple of examples are here and in the next page. So here I am asking to find inverse Laplace transform of 2 over s to the 4 minus 6 over s squared plus 4. So this is easy question, you can use the table. So can you take a minute and find the answer? So if you are done, actually you can try the other two questions as well. So you may want to use the table. So take a small break, 5 minutes. Okay, so in this question, maybe you have done. So you can straight away apply the linearity here. You can take these 2 out. Then this is the inverse Laplace transform of 1 over s to the 4. Okay, so you can take this 6 out. So minus 6, inverse Laplace transform of 1 over s squared plus 4. Okay, so if you look at the table, you need to again locate a similar. So you should look at the right hand side of the table and do that. You take 1 over s corresponding to the polynomial number. And then you have this form, say constant of s squared plus k squared. So that's corresponding to sin kt form. Okay. So if you look at these things from the table, you should see if you put factorial 3 here. So factorial, if you put this here as 4 here. So if you do this, you have to divide by factorial 3. So you need 2 here. So this is s squared plus 2 squared. So if you multiply by 2 here, you need to divide by 2 here. Okay. So this is simplifying. After simplifying, this will become 1 over 1/3. This inverse Laplace transform straight away from the table, and this is t cube. So this is 3. This inverse Laplace transform is sin 2t. Okay. So you should see the inverse Laplace transform. Next question. So again, given this may be going to be our friend exponential function. So we want to find inverse Laplace transform of this function. So 1 over s squared plus 3s minus 10. if you do partial fractions, sorry, actually here 3 is there, right? Can you do the partial fractions here? So first do factoring. So if you do factoring, I think s minus plus 5 s minus 2, right? So you do partial fraction, so you need find this constant. So find quickly the two constants. And you can check this table, do you have that kind of thing? So if you go here, I don't think you find exactly similar form, right? You can see, but instead the denominator most of the time it is factored, right? So you can here s minus a, s squared minus k squared, s minus x minus b, or these kind of factors. You don't see that polynomial form in the denominator. So that's why we want to factor the denominator. So when s is minus 5, you can find a, right? Excuse me. So when s is minus 5, this will become minus 3 over 7. So then if you put s equals 2 here, except for s minus 2, you get 7, right? 3 over 7. Okay. So that's the partial fraction. So which means you can write this one as inverse Laplace transform so we just found this to be minus 3 over 7 s plus 5 3 over 7 s minus 2. So now what we do, we use linearity. So this constant you can take out, minus 3 over 7 inverse Laplace transform 1 over s plus 5. Again 3, 7 you can take out. So inverse Laplace transform 1 over s minus 2. So if you check the table now, for the inverse Laplace transform for this function, you will find So here we have exponential at Laplace transform is 1 over s minus a. Now here we have 1 over s plus 5. Okay, so which means a is like minus 5. So here the inverse Laplace transform is going to be exponential minus 5t. Okay, plus 3 over 7 s minus 2. Now here a is 2 exponential 2t. Okay, so now if you look at the next one, if you try to do the same thing, you will see this, you cannot factor that. In that case you can, what you call, you can complete square. Okay, so here the given function f of s for s over s squared plus 2s plus 5. So again, if you straight away, if you look at the table, you will not find this function straight away. So that's why you need to do some manipulation. Okay, so if you try to do factoring partial fractions, you will see it won't work. So if you complete square, this is another way to do. So you have s squared plus 2s plus 1. So here you need to add 4. Okay. So okay, now let's come back to this question little later. Okay, little later means we will do what we call shiftings right now. So after we do this, you can try that earlier question. Okay. Okay, now these two shifting theorems, so shifting S and shifting T, going to be very useful. Now, so what this S shifting theorem tells us, so if the given function, original function little f, Laplace transform capital F, so if you see something original function being multiplied by exponential function here, exponential minus at, in that case, once you do that, what's happening, the Laplace transform, it will be shifted, so it will be shifted to here, to left, by saying a, you multiply by exponential minus a, this should be actually s plus a is greater than 0. So for this kind of theorem, so mathematically this is not difficult to see. Okay, so kind of a proof. So how do you calculate Laplace transform? Now this is something you can do. So if you understood so far, so here what you do, integrate 0 to infinity. So exponential minus st, exponential minus at, f of t dt. So what is this? So integrate 0 to infinity exponential, if you take minus out, s plus a t f t dt. Okay. So what can you say about this integral? Now note that a is some constant. So in this integration, s also constant. So we have to remember how we define our constant. So if this s plus a is constant, then the integral is the so this is nothing but the Laplace transform of capital F. Now this is f of s plus a. Okay, provided, so for the convergence you need this s plus a to be strictly greater than 0. Okay. So if you remember what we did last week, now here, note that what we want to find is t cubed exponential phi t, that's the given function. So Laplace transform of t cubed exponential phi t. So you want to find the Laplace transform of this. And it is given Tn, this is the Laplace transform, which means that part will be available in the table. Okay. So now in the example, we try to do this by So here when n is 3, so Laplace transform t cube, so you have factorial 3 over s4. So what is this then? So I've done, because here this is just one step answer. And this is okay, so I'm not sure, but I will write. You are done or not, I don't know. So you are multiplying by exponential phi t. If you multiply by exponential minus at, so all you have to do, instead of f of s, the Laplace transform is going to be f of s plus a. Now a is here like minus 5, so this is going to be f of s plus minus 5. So f of s minus 5. So what is that? So this is f of s is factorial 3 over s to the 4. So this is going to be factorial 3 over s minus 5 to the 4. Okay, so that's the answer. So here y, so a is minus 5. Okay. So now you see you don't know what to do. Okay, now here is can have a 10 to 0. Those are called T-shifting theorems. Now note that here you can express this in either form, as a Laplace transform or inverse transform. So here, which means if you have a inverse Laplace transform, so if you identify something as f of s plus a, and if you know f of s is the Laplace transform of f of t, the inverse Laplace transform is going to be exponential minus at f of t. Okay. So I here put actually on one form, but it is valid for both directions. Now T-shifting theorem I have written in both ways. So if the Laplace transform of f, little f is capital F, so then if the original function was shifted by a units, let's say here to right, thinking as positive, so it doesn't matter, because to make this rigorous I have put the Heaviside function, so ht minus a, so before a everything is 0 now. So what's going to happen, all you have to do, multiply your transform function by exponential minus a. Okay? So same thing written in a different way. If the inverse Laplace transform of capital F is little f, then if this is the thing you want to find, say you may know what's the inverse Laplace transform for f from here. So in right, but if you have exponential function being multiplied exponential minus sa, then all you have to do is shift the original function by a units. Okay. So question here. So given function is f of s. So s minus 2 exponential minus 3s. So we want to find little f. So here also let me give you a quick proof. So let's start with the Laplace transform. So this is ft minus a, ht minus a. So integrate. Now note that this means, this notation tells us the function you multiply, say given function is f of t, you shift it and multiply by so integrating from a to infinity. So exponential minus st ft minus a dt. Okay, now here use a substitution. Let's say you use t minus a to be x. Can you do this substitution? So what are the limits? So when t equals a, you get x equals 0. T goes to infinity. So it doesn't matter, x goes to infinity. And dt is dx. So this is now equals to 0 to infinity. Exponential minus s, t is x plus a. So f of x dx. So s is constant, now a is constant, so exponential minus sa you can take out. 0 to infinity exponential minus sx f of x dx. And what is this? So this is exponential minus sa, and this is the Laplace transform of little f. Okay, so variable of integration is a dummy variable. I keep writing t because usually it is time, but you can write t or x or y or anything. Okay, so again a very cute proof. Okay, now if you had any doubt, if you are suspecting what I am saying, you don't have to do that anymore. So this means exponential minus 3s log y squared original function. So we know, if you now so far you should remember, if you have 1 over s squared, what was the function earlier you saw? From the table you can see, from your, I think you may remember by now, if you take Laplace transform of t, you get answer to be 1 over s squared. Right? So in other words, inverse Laplace transform of 1 over s squared is t. Okay. Now some of the play write it as A is 3, right? So this is going to be ft minus a so you want to find inverse Laplace transform exponential minus 3s y squared. So what's the answer? Well, now here a is like 3, so this is going to be t minus 3, shifting 3 units. Okay, so technically this is going to be more precisely t minus 3 ht minus 3. But even if I don't write this, you should know this is valid for now when t greater than 3. Okay, so earlier I left one question this side. I think do I want to do this, or maybe I leave it as a homework question. So when you do this, now you can see you are seeing this s plus 1, right? So this is being shifted now in the s domain. So well, I'm going to leave this as a homework question. So use shifting. Okay, so this is the next topic, what we call convolution. Okay, now for these two variable functions, the derivative function is actually more than this is convolution. So this is a definition, and f convolution g, now note that f is a function of time, g is a function of time, and once you do the convolution, f convol g also a function of time. Okay, it's a function and domain is still t. So which means my variable of integration is a dummy variable here, and it can be anything. Now here I have written as x. So take one function, say f, and you shift it by x unit. So t minus x, then multiply by gx, then integrate in general from minus infinity to t. Right? So when you have a convolution, this is the general definition. So but for the Laplace transform, this is going to be integration from 0 to infinity. Okay. So f convolution g, this is going to be 0 to infinity f t minus x gx dx. This is a function of time. So only difference is with the lower limit. Okay. So because even if it is, we are going to integrate from minus infinity to t, minus infinity to 0, everything is 0, right? So nothing to do. So okay, now we have two functions. Now again, this is just an integral, right? So if you are nothing to be so the question is, we are asking the given function is c, now even if I don't do this as cht and t square ht, in other way to do it, I can do it as c and t square k is more than you don't need to worry about it. Convolution f. So what is, let's say, f convolution g? So if you want, we can write this as function of t or not. So it's anyway going to be a function of t. So let me just write it. So how we solve this? Integrate from 0 to infinity. F is t. So what I need is not ft, I need f of t minus x. So if f of t is t, then what is f of t minus x? So t minus x. And gt is the same thing. If gt is t squared, gx is going to be x squared dx. Can you quickly do this integration and see what's the answer? And if you are done, try g convolution f as well. So in this integration, t is constant. is, yes. So when you have f of t as th of t, but in general, this is what you have, right? So if you have t axis here, y axis here, if you have this is, say, y equals t. But when you say y equals tht, so this will become like this. It is just to say the negative side is 0. Even it is not there, you should know your answer should be the same. Exactly, we will do the exactly same thing. So ht is the heaviside function, right? So we studied last time this kind of function. So this is ht. So if you do this integration, this is not 0 to infinity, 0 to t. Okay. So in convolution, 0 to t here. Sorry about that. So what you have here, 0 to t, so this is tx squared minus x cubed dx. So t is constant, right? So you have t x cubed over 3. So your limits are 0 to t. So minus x4 over 4. So limits are 0 to t. So put the limits. When it is 0, everything is 0. So I think answer is t4 over 12. Okay. So note that this is a function of t. Okay. So calculate the other one as, and this is f convolution g. So g convolution f, calculate that one. It's going to be a function of t. So quickly do that and see what you have. read the note, you will see we are saying this is commutative, right? So which means order doesn't matter, f convolution g or g convolution f is the same. But let's check it, at least for now. This is not a proof, just a verification. So when we want g convolution f, now g is x squared, sorry, gx is gt is t squared. So what we need is g. Now here note that this is going to be 0 to infinity, sorry, 0 to t. So gt minus x f of x dx. Okay. So 0 to t. So gt is t squared, so gt minus x is t minus x squared, and f of x is t. So f of t is t, so f of x is x dx. So what is this integration? So again, this is easy to do integration. So here we get t squared x minus is plus x cube dx, right? So this integration you can do, so just algebra part. So you get t squared x squared over 2 minus 2t x cube over 3 plus x4 over 4. So limits are 0 to t. So do your algebra, you should see, you should get the same answer, which is t4 over 12. Okay. Now for this convolution, there are actually very nice properties. Maybe I should mention a couple of them. So one we already saw. Okay. So one is f convolution g is same as g convolution f. So which means convolution is commutative. And actually this is associative too. So which means if you have, you can shift the order. So you can emphasize this one here or this one here, it is the same. So this is to say this is associative. Actually distributive property is there. So if you have f convolution g plus h same as f convolution g plus f convolution h. So this is distributive. So if one function is 0, what can you say? What is f convolution 0? So this is the 0 function. F convolution 0 is function. So here maybe you may need to note this is not the product. Okay, so of course if it is the product, why I have to use a different name and a symbol, right? So to see that, let's say for example so let's say your f of t is sine function, sine t, and take g of t to be just 1. So find F convolution G. So can you quickly find this? T. So we are finding F convolution G integrates from 0 to T. So first function sine function is shift sine t minus x. Second function gt, so gx is still 1, and integrate say dx. So what is this? Sine t minus x, now here t is a constant, so this is minus cosine t minus x. So a variable of integration minus x, so it's substitution, otherwise you should know you have to divide by minus 1. Variables are 0 to t, and put the limits. When x is t, cosine 0 is 1, so you get answer to be 1. X is 0, so this is minus cosine t. So note that this is not same as sine t. So this is just to confirm convolution is not the multiplication. Okay. 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 Now let's see. Okay, now here's an important theorem. So this tells if you have two functions f and g, and if you know the Laplace transform for both of them, then if you want to find the inverse Laplace transform of the product of those two functions, now this is the real use of convolution. So if you have one function, all the forms. So this is an important theorem. So we want to find inverse Laplace transform now. Inverse Laplace transform of 3 over s squared plus 3s plus 3s minus 10. So using convolution, so I mentioned earlier this earlier question can be done. I mean, if you remember, this is the question we did before. So now I'm saying earlier, so this is inverse Laplace transform 3 over, so it's going to be s plus 5 s minus 2. So now we know from the linearity we can take this 3 out, so inverse transform, now we have something like this, s plus 5 s minus 2. So this 3 is, it will stay outside. Now if you look at these two functions, 1 over s plus 5, 1 over s minus 2, you should see by this time these are Laplace transforms of some known function. The inverse Laplace transform for, if you take just one fraction here. So theorem tells you can write this as inverse Laplace transform of 1 over s plus 5, not the product, as a convolution inverse Laplace transform 1 over s minus 2. Right, so this is the convolution. So if you know these two things, all you have to do, convolve them, which is an integration, and sometimes it can be quite easy, sometimes it can be difficult. So answer going to be, so what's the inverse Laplace transform? If you are not sure, you can look at the table. When you have s plus 5, it is exponential minus 5t. So convolution, this is exponential 2t. Okay. So earlier you did this same question and you got some answer. Now maybe 15 minutes convolution, if you don't So here 3 should integrate 0 to t. This is easy integration. So to your integration you should get your answer to your algebra part here. So 3/7 okay, after putting the limits. So check with this earlier calculation, so it should be the same answer. Exponential 2t minus exponential minus 5t. So this is what we had. I mean, if you factor out, you get the same answer. Okay. So that's pretty much you need to know about convolution. Now, if you look at this Laplace transforms, say if you do the transformation 1 you will run over x and 2 you will run over x square. Mention this. So if you check your table, so note that this is the Laplace transform. Now when you have 1 here, so your original function, this is called delta function, delta t. Okay, but maybe you don't know what delta function is, so that's why I just want to mention at this point about delta function. Now if you look at this definition, so this is little bit strange, right? So we are saying some number, let x minus 0 is equal to So what we do, so let's say for simplicity, so let's say a is 0, okay. So let's consider this function. Now in this case, well, what you really get is delta x to be 0 if x not equal to a, so 0, and infinity if x equals 0. And we have integrate minus infinity to infinity delta x, this area is still 1. So if you try to draw, well, this part is clearly 0, this part is clearly 0, and I cannot draw this. So actually in practice it is some large number, you can have some sort of spike or something. So the reason you do this is, in say electrical, you may have so here, but I should need to tell, so this is not really a function. So this is actually what we call a distribution. Distribution, or sometimes called a generalized function. Distribution is not the distributions you studied in statistics, so separate theory. So let's say generalized function. So generalized function is not a function, need not to be a function from the way we have learned so far. Right? It's some advanced theory, so you don't need to worry too much, but I will give you some idea how to construct this. So let's say we have this kind of, let's say t is here and y is here. So let's say this value here is, this length is L, this length is minus L, and I need this area under this curve to be 1. Right? Somehow if I integrate minus infinity to infinity, I need area to be 1. So what should be the height here? So height should be 1 over 2L. Okay, so that's the height. So note that now for any, if you take any L which is non-zero, if you integrate this minus infinity to infinity, so let's say this function is f, so ft dt, so this integral is 1, right? Now area is, height is 1 over 2L, length is 2L, multiply, answer is 1. Okay. So then what we are going to do, we are going to make this L very small. So we let L approaches 0. So in a diagram, so graphically this will look like, so if you start with something like this, so this may be your first L, and let's say you make it half, so you need to increase the length here, so you may get something like this, and something like this, and something like this, So this is t, this is y. So when this L approaches 0, so you started from here and you make L very small, so what's happening to the function? When L becomes very small, the area of omega has to become very small. So L is very small, you can see it becomes very close to 0. So the limit, what we call the limiting distribution, will be the delta function. So as L approaches 0, you get what you call the delta function. Okay, and note that you have the properties. So delta t, so this will be 0 for t not equal 0, and if you integrate minus infinity to infinity delta t, so area still remain 1. Okay, so how are we going to show this? Maybe if you feel a little bit uncomfortable, so let me give you a little sort of proof. So note that if you integrate minus infinity to infinity, so delta function, delta t dt. So we can write this as, say, minus infinity to infinity so one height is, say our height is 1 over 2L. So using the Heaviside function, you can write this as h t plus L, right? So which means this is shifted L units to left, and then if you subtract h t minus L and multiply by 1 over 2L, so that's the height. So this is pretty much the function. If you are integrating minus infinity to infinity, everything less than minus L now is 0, and after L also this is 0. Height in the between minus L to L is 2L, so that's what is written here. So integrate with respect to t, and here if you take this limit as L goes to 0, so this is what we want to calculate. Now simply this is nothing but, say, limit L approaches 0, so minus infinity to minus L function is 0, so I am not writing that part. So this is going to be minus L to L, so 1 over 2L, and this side is, this is just 1 here, and this is just dt, and then again L to infinity function is 0. Okay, so this is, if you do this integration, t integration, so L minus L becomes 2L, so if you cancel 2L to 2L, this is just 1, so you find the limit L approaches 0, 1 g, sorry, this is just 1. So this area is just 1. Okay, so I didn't write like many steps, so you can check it yourself. Okay. So which means this is, well, at least mathematically, we are proving the area of the base of the electron. Don't get upset. So that's the delta function I showed you a few minutes ago. When you wanted to calculate the Laplace transform of this function, you get this constant function which is 1. Okay? So that's why because it is in the Laplace transform table, I just want to show that. Now one of the important thing is called the shifting property for delta function. This is actually a very important property. So what this is telling us, you take the delta function and you multiply the delta function If you are still not convinced, I can give a small proof, but I don't know even if I give a proof or not. Say for a shifting property, so what we are saying, integrate minus infinity to infinity this function f of x be multiplied by delta x minus a. This is a delta function dx. So this is same as evaluating function f at a. Right, very nice property. So here's a quick proof. This is not the very rigorous proof, but I think you can be able to follow. So you start with this minus infinity to infinity f of x delta x minus a dx. Now note that delta function is 0 when x not equal to a. Okay, so everywhere except that point this function is now 0. So if I integrate minus infinity to anywhere close to that number, that part is 0, so I don't need to worry about, right? So I can write, so I simply integrate a minus epsilon to a plus epsilon. Now epsilon is a small number, so you may not be used to this kind of notation, so don't get upset, but this will finish, will be over very soon, with a very short proof. Okay, so you have f of x and delta x minus a dx. Okay, now what we are going to do is, inside near this interval f of x, because function f is now very close to a, so we are going to say if you evaluate f of a, this is approximately same. So you can take that out, and then you are going to integrate a minus epsilon to a plus epsilon delta x minus a dx, and this integral a is what? This is simply 1 by our definition, and we proved it. So this value is now f of a. So this is a cute little proof, not the very rigorous one. Rigorous one is advanced proof, but you can get the idea from here. Okay, so I just want to, because I really don't like just giving things, okay, this is this, you remember everything, but whenever possible I try to give you some justification. I'm not sure how, up to what extent you follow this, but if you are the person, it bothers you when there's something without a proof, without justification. So for those people, so you can have this, you can go through and see. Well, if you don't care, anyway, then doesn't matter. Okay, now here's an exercise. We want to find minus infinity to infinity exponential function ex multiplying by delta x minus 1. So we want to find that limit, sorry, that integral. So can you do this quickly? Ex delta x minus 1 dx. So what is the answer for this integral? So if you are done, then find try number 23 as well. So take a minute. So you are simply evaluating exponential function at 1. So this is e to the power 1, which is just t. Okay, very good. Now can you try the next one? So find the Laplace transform of delta function. So find this one. So first do that part, and then after that see what is let's assume A is suitably placed. Okay. So integrate 0 to infinity. What do you do? Exponential minus st. This is the delta function, delta x minus a t. So now here I wrote in x, so maybe I should change this to x. So x is our dummy variable, right? So far I was writing t, but here maybe I have written x. So what is this integral? So this is how much? So note that our assumption is this A is suitably placed, which means A should be between 0 to infinity, somewhere there. Okay. So in that case, the answer is exponential minus SA from the shifting property of the delta function. Now to deduce this part, what you can do? So note that. So if you choose A to be 0, now delta function, let's say this is centered at 0. So in this case, you are getting Laplace transform of delta x. When A is 0, this is exponential 0, which is 1. So this implies inverse Laplace transform of 1 is the delta function. Okay. So this is what you saw in the table at the beginning. On the paper here. Okay. Okay, now what we have next is another important thing. So this is the prelude to differential equations. So when you want to solve differential equations, we need to deal with derivatives. But things are quite similar because big difference, but there are things you need to be careful. Now, so in this theorem we are saying if f is continuous, f prime is piecewise continuous, and so f is of this exponential order, all the conditions are there. So the thing is, so we are finding the Laplace transform of now a derivative f prime. Okay. So we are saying the derivative of, Laplace transform of f prime is s times Laplace transform of f minus f0, which means the, what is it's an initial value. Okay. So second derivative f double prime, when you want to do the Laplace transform, you can identify some sort of pattern, s squared Laplace transform of f minus s f0 minus f prime 0. And in general, nth derivative, you have this formula. This is the, you start with Sn, Laplace transform of the original function f, then all the things are minus signs, Sn minus 1, this is the power, times f0, then Sn minus 2, evaluated the first derivative at 0, and likewise you go ahead until the powers of s will reduce until here when s0, which is 1, derivative f, order of derivatives, they are increasing up to n minus 1 when you take the Laplace transform of nth derivative evaluated at 0. Okay. Now general case I don't want to prove, but I want to give you some idea about this, at least for this part. Okay, so this part is important and the second derivative part is important. Okay, so because most of the time when you solve differential equations, you either solve first order equations or second order equations. Okay. So let's see quickly. So what's the Laplace transform of this first derivative f prime t? So can you calculate this real quick? So what do you do? Integrate 0 to infinity exponential minus st, now f prime t dt. So this is, so do integration by parts, quickly do the integration by parts and see what you get. So you have derivative, so you can integrate that part. So exponential minus st ft, and limits are 0 to infinity. Then you have integrating 0 to infinity. So this is ft minus s exponential minus st dt. Okay. So note that this is f is of exponential order. Now as usual, if you remember our argument last week, when t goes to infinity, this integral goes to 0. So that's the point of the taking a function of exponential order. When t is 0, exponential 0 is 1. So this is, you are going to have here minus, well, this is 0 minus f0. Okay. So then here you have plus s 0 to infinity ft exponential minus st dt. And what is this? This is nothing but Laplace transform of f, right? So this is f of s. So this is f of s minus little f0. So that's what you have right here. Okay, so this is same as s f of s minus little f0. So that's what we prove. Now if you want to prove the second derivative, you have to, all you have to do, use the same thing, same procedure, and you have to keep doing it for higher order derivatives. Right? So you can see once you do couple of times, so if you have time you better do that and see, there you will get this pattern here. Okay, now to conclude today's lesson, so here I am asking to find the Laplace transform of function f of t. Note that the given function, given equation, now this is actually a differential equation. So what you have here, f double prime t, second order derivative, minus f prime t equals to, this is a differential equation of second order process. Now what ask you to solve this? Let's ask you to find the Laplace transform of the function derivative. So that derivative equal to f of s equal. So what you do is you know how to differentiate. You can always do the equation, but you can do as much as you can. So we equal the only equation when higher than 0, or the average equation given in the like So basically we are doing applying the linearity, Laplace transform of both sides equals so if two functions are equal, their Laplace transforms are equal. Then apply the linearity, so here Laplace transform f double prime t, Laplace transform f prime t, so Laplace transform 3t, or if you want take 3 out t. Okay, so this is given in this equation. Second derivative, you have s squared Laplace transform f of t minus s f0 minus f prime 0, then minus f prime t Laplace transform, which is given here, s Laplace transform f of t minus f of 0. Then 3 times Laplace transform of t is 1 over squared, so we can have 1 over squared here. Now you should see what we are asking to calculate is this guy. It is here. f0 is 1, so this number is 1. f prime 0 is 0, so this number is 0. f0 is 1, so this number is 1. So this is just algebra now. So this is the power of Laplace transform. Write the answer. So if you simplify now, here you will get, now note that I can write s squared for to make it short, capital F for the Laplace transform of little f, fs, so all you have to do now, solve for capital F here. So f of s will be so do the algebra part. This is s cubed here and s cubed s minus 1. Okay, so that's the answer. Okay, so now in the next week we will look at the applications, which means when it comes to differential equations, how you going to solve Laplace transforms now using the differential equations using the Laplace transform. So you better look at differential equations when you come to the next class, then it will be, things will be more clear. Okay, so thank you, and I will see you next Thursday.